Welcome to another episode of James Explains, where today we're taking a look at the fourth of Matt Parker's maths puzzles. Have a look at the video for yourself if you'd like to see the full puzzle, but for those of you who want the quick version, we want to find the lowest possible number of card flips from any unknown combination of face-up and face-down cards to get all cards face down at the same time without ever knowing the current state of the cards. Let's look at an example of possible starting position. We can see that to reach this starting position from all cards being face down, we need to flip the second and third cards, but not the first and fourth. We can also see that to get it back to all four cards being face down, we again need to change the state of cards 2 and 3, but not 1 and 4. Therefore, we can think of this as a binary state with an unknown binary offset, where we need to replicate the binary offset to convert it back to the desired position. So, with 4 bits to work with, we have 16 different values that can be represented. This means we require 15 steps to cycle through these 16 values. However, normal binary counting is not an efficient way to cycle through all these values if we want to reduce the number of individual swaps to be made. For example, going from binary 1 to binary 2, we need to turn the third bit on as well as turning the fourth bit off. This means that our 15 steps would require 26 individual swaps, looking somewhat like this. But there is another binary counting method that would help us achieve these 15 steps using only 15 swaps, so we don't have to complete all these swaps to cycle between the 16 different states. This method is known as Refelcted Binary Code, but is also sometimes known as grey code. This type of binary counting was developed to avoid spurious outputs from electromechanical switches, but is still used today in digital communication for error correction. Let's look at an example of switching from binary 1 to binary 2 using the normal binary counting method. This requires us to switch 2 bits at the same time, which is not always straightforward if using electromechanical switches. If there is any small delay between the switching of the bits, we will temporarily get spurious values. If we turn off one bit before we turn on the other, we will briefly get a value of 0 before we get 2. On the other hand, if we briefly switch on one bit before turning off the other, we will briefly get a value of 3. If instead we were to count with grey code, only one bit switches at a time, and we're able to cycle through all possible values. But how can we arrange our bits to allow us to count like this? Starting with one bit is quite easy, as we're only switching between the 2 values of this bit. If we introduce the 2-bit method we just saw, then you can begin to see how this pattern develops. If we look at the bit pattern for 1 bit, we can see that this pattern occurs in the least significant bit in the first 2 values of the 2-bit pattern, and then it is reflected in the last 2 values. We can try to take this same approach and see what we get for 3 bits. Firstly, we take the 2-bit values. Then we reflect them. We then add leading zeros to the first half and leading ones to the second half. And we have the grey code pattern for 3 bits. This same approach can be taken for 4 bits, 5 bits, and so on. One thing that is interesting to note is that the pattern for every low number of bits can be found in an initial subset of any given pattern. What this means for our card puzzle is that we don't even need to know how many cards there are. We can continue this pattern and simply expand the bit length by 1 every time we have completed all possible values for any given bit length. We can also say that for any given number of cards, there are 2 to the nth power of possible values we can test. This means that the worst case scenario for any given number of cards can be solved in 2 to the nth power minus 1 moves. But what if we don't just want to get them all face down? What if we want all the cards to face the same way? Let's start off with just a single card. It can be either face down or face up. One thing we can see though is that we have already won, as with only one card we know that the whole set must always be facing the same direction. So now, let's ignore the position of this first card and look at the rest of the cards in a larger set. We know that cycling through all possible states for the remaining subset of cards will at some point reveal the state of all face down and the state of all face up. Given that at least one of these states must match our unknown first card, we can see that the process for arranging all cards in the same orientation requires exactly the same approach as trying to get all cards face down for a set of one size smaller. Therefore, if we only want to get the cards in the same orientation, the worst case scenario can still be solved in 2 to the nth minus 1 power minus 1. If you would like to see the original puzzle, or others like it, visit thinkmaths.co.uk/mathspuzzles. And if you would like to see videos on any other concepts, leave a suggestion in the comments down below. As always, thanks for watching.